This is you guys? No.
No.
So any of you tried yesterday?
Yeah.
The CIS exam? You did. How did it go?
No.
Not good. There were other couple of guys, right? How many? 3 or 4 of you tried?
3.
There are people going tomorrow? There will be 5 people.
Tomorrow is the exam for particle physics, right?
I don't understand what they replied, but I think I cannot take exam.
So as I said, sorry, as I said, you don't have to do the homework before Monday, but it will help if you have a look for Friday. Just if you have a look, you don't see what it is, because certain things a little better. So how many are we missing? 3.
3.
Maybe on the bus.
Yes.
No, I guess they
there are
have
2 interviews
with CISA.
Oh, they're having interviews now.
Yes.
With CISA.
So there are 1 that's missing.
He's here.
So that means they did okay in the
Yes.
written part.
Yes.
And now they are.
Yeah.
All right. So it's too bad that they are missing that. We could have arranged for that. It seems that you are free some afternoons, right? We could have moved the class. Like on Friday, the class is being moved to 2 o'clock.
Yes.
There is some meeting.
But we have a GR at that time, but this week the professor is not here. So that week, that's why.
Like today afternoon.
No, we have a GR this week.
All right. So let's start. So what we want to do, it's probably, I'm probably too conservative. I want to teach you the art of conservative speculation or speculative conservatism. And it may not be necessary after all. A number of you are doing string theories and extraordinary speculation, which has nothing to do with any hint of whatsoever theoretical or experimental. Even theoretical, if you think about that. The string theory came about when, at the peak of the success of field theory. All we have today is field theory, okay? Not a shred of evidence that we should go beyond. But still, even if you guys are maybe not conservative, maybe at least some of you, I want to teach you this delicate art of keeping your feet on your ground, but then still trying something new, because this is how the standard model emerged. There have been many wild speculations that died meanwhile, and there will be conservative approach that disappeared, you know, got extinct as dinosaurs. So what we have to do is try to understand why the years, let's say the era is 50s, and this is a time when the QED is going through a great success of making high precision statements. And so I'll come to 1957. At that time, what is established is the form of weak interaction. Finally, a ground-breaking work of Marshak and Sudarshan establishes, and it's a beautiful word because it says that in spite of the experiments, some of them being against the statement I'm going to make, they are arguing that this must be the form. And around the same time, Gelman and Feynman will suggest, purely on sort of aesthetic grounds, this may be the reason why they never got the Nobel Prize, okay? I'm going to mention the non-given prizes, okay? Because everything that we have today. Some few years ago, Weinberg gave a beautiful review of the supporters of the work, and he said, V minus A, there is a nice paper to read, was the key. He could even put an exclamation mark. Okay, this is Weinberg's. These people come out with what is known as the V minus A theory. It's the final word on the form of weak interactions, and we know that the effective Lagrangian for weak interaction, it is effective. As a G Fermi over 2, let me now be careful, and it has the form of the, why don't we write? No, let's write like this, G mu weak, G mu weak dagger, where G mu weak is, I'll write in the form of quarks. Of course, that time there was only proton and neutron, but let's use the modern language, okay? So we have U bar, gamma mu, 1 plus gamma phi. Remember, don't worry about the sign here. Gamma phi itself is not defined up to a sign. D plus the weak interactions are universal. This is beautiful, okay? Quarks and leptons have the same form. And this helps it tremendously, okay? So this is nu bar gamma mu 1 plus gamma phi E. Am I right? The charge is okay, right? This is charge -1. Okay, we have to remember that Q up quark. Sometimes I may confuse myself, not only you, I use a capital letter for charge, sometimes a small letter, okay? Typically what we do, typically what I should be careful, when I write Q electromagnetic, it's sort of an operator, which of course is diagonal. It's a matrix which is diagonal, which is a collection of charges. And if I'm careful, I should use small q for charges. So Q electromagnetic would be a matrix with all the charges, Q up, Q down, Q electron, and so on. Okay. The order is not so important, but this is a U1 theory. There are no commutations, there is no quantization in it. Okay. And you and I have to remember that in our units, QE is -1, Q neutrino is 0. These numbers actually are good to a fantastic precision, in less than 1 in 10 to the 20. For example, no, the first number is just a normalization, right? I can put anything I wish. But the second, with a great precision, neutrino is neutron, for example. And Q up is 2/3. And Q down is -1/3. That's all what you need. For quite a while, for another couple of weeks, 3, 4 weeks, I don't know, I'll pretend that there is just one generation of fermions, what we call, right? There are no other guys. Okay? I'm sure you know from Alexei's course. That we have a plethora of other particles. But they're kind of irrelevant. What I'm talking about is what the universe is made of. If we were not restless, if we didn't build these machines, right, that we sort of break things apart, smash things apart, it's like, you know, we trying to understand what it's made of and then hitting it against the wall. That's what we do. We wouldn't even know that there are other guys, right? The universe is made out of this. So when I say to good precision, what I mean here that the charge of the proton is +1 and charge of the neutron is 0 to a good precision, great precision. This is often written in the following form as 2, there is a factor of 2, of course, UL gamma mu DL. It's a more compact notation, UL gamma mu EL. Where obviously L projector and right projector in my notation here are these. And they are projectors because gamma phi squared is 1. They are projector in a sense that L square is L, right square is R, and they are orthogonal to each other. And as you know from the homework, okay, and we'll be talking about that next week, and the parity left goes to right, just as my left hand goes into my right hand.
Why 2?
Because I don't have a 2 here. But
okay.
oh, without a 2, it wouldn't be a projector.
Okay.
You wouldn't get it back to itself, it will give you an extra factor of 4 or whatever.
Yes.
Okay. That's not wrong. So I guess you meant, why do I define it by half? So that I have this. And you know, this is an interesting area of the air. This is just about, was established, and it was established that the world is purely left-handed just because a year before, actually towards the end of that year, by the end, it was at the end, in December of 1956, that the experiments will confirm the bold suggestion of Li and Yang that parity may be broken. It's interesting, I don't know if you've ever seen pictures, you should, you know, click the Li and Yang pictures, and after they get the Nobel Prize, they look younger than you guys. Partially because they are Chinese and there is this tendency that they look younger, you know, it happens to me, you know, I have close friends, I spend a lot of time in Taiwan, I visited China, and I always get fooled by the age. But still, they were kids basically when they got prizes. Didi Li may not have been 30 years old. It was such a revolutionary statement. Now why? But because we got so used, the world, everybody, that it should be symmetric. Okay. Then the violation of that was dramatic. If there was no prejudice that the world had to be symmetric, it wouldn't have been such a big deal, right? Well, life is like that. And what it says that I have only left-handed guy. If I wrote the complete theory, which was not crippled, then I would have equal amount of left and right. There would be no gamma phi, okay? This would be like QED, okay? But notice there is a difference. Otherwise, it looks just like QED effective Lagrangian. Except that GF is a small number in the units of something. It's small in the units of 1 over Q squared, which Q would be the energy of that air, or 1 of the energy squared. It's small in the units of 1 of the electron mass squared, which was relevant, okay, at that time. So I can say, when I say small, this is much smaller, say that 1 over ME squared, roughly the time of the energy of weak interactions, okay, the reactor energies around MEV. The energy that relevant for neutron decay. Why is that energy relevant for neutron decay? After all, neutron and proton are very heavy particles. Let's see how much you remember mass scales. Mass of the electron is 0.5 MeV, I'm sure you know that. So what is the mass of the proton, which is basically equal to mass? Okay,
1 GeV.
Right. But you see, here is the catch.
Neutron and proton.
Neutron and proton, here is the catch. They're almost equal. The mass difference is of order on MeV. So MeV is the relevant energy, okay? Because neutron has to decay, right? Weak interaction, after all. What is weak interaction? Of course, there is another weak interaction. You can tell me the energy is somewhat bigger. For example, if muon decays, but I'm pretending there is no muon at the moment, okay? Muon is another electron, okay? But still, let me mention it. It's still a small energy, so muon will decay into E. Remind me, how does muon decay?
Electron plus neutrino, electron.
Neutrino.
Very good. Antineutrino. Well, the energy here relevant for the process will be somewhat bigger. It's basically the mass of the muon, because these guys are basically massless, okay? Neutrino, of course, but even the electron compared to the mass of the muon, which is 100 MeV. So I could write this if you wish. It's much smaller also than 1 over mu squared. It's really small. Okay. And there is no hope that you are going to be doing soon experiments at very high energy. So why would you modify this? Well, one answer is, of course, why not? And why am I bugging you with that history? Such a distant, remote history, right, from everything today. We've been living this for a long time. I can't help it. Well, according to this picture, you know, this would be sort of Newtonian, although Newton himself believed that there ought to be messengers between forces. But here is an example of a force which has no messenger, it just happens. And it's sort of not so appealing. So a desire to make the world more, if you wish, physical, more deeper, more appealing to what is everyday experience is when we interact with each other, they're always messengers. They're sound waves, whatever they are, radio waves, whatever, touch. So one, it is surely, you know, at the same time, in the 50s, we have an emergence of QED, which is a very different theory, in which the interaction is psi bar, gamma mu, Q, phi, A mu, with some strengths which I call E. Notice please that there is not so much importance to attach to E or to this. I could always renormalize the charges and renormalize Z, okay, what appears is the product of two of them. So E is relevant in the units you and I fixed. Okay. And I have no knowledge or why this number is what it is. All I know is that E squared over 4 pi is at that time 1 over 137. So the theory was more appealing. It had a message there, of course. What else? It was even more important. Why is it that we people believed in QED? Because you could make high precision statements. How did we make those high precision statements? In perturbation theory. How do we do perturbation theory? In Feynman picture. One simple word is loops. You did loops? Scalar theory?
Yes.
Okay. That's all I need. You didn't study renormalizability.
Let's do it this
Well, I'll
way.
give you a feel. Let me give you a feel. Let me. Okay, I'm gonna get the introduction to Saif. Let me give him some introduction. Let me give you a feel of what it's all about. Okay, it's a fancy word, and it's a lot of technique, but it boils to what I'm gonna say now, and it has to do with the following. If I want to do QED, this is the Feynman picture, right? I have
Yes.
fermions, and we follow it. Electron, you can't break the electron line. Charge is conserved. Electron number is conserved. And then I have a photon. Loop means that in whatever process I do, there ought to be a correction, a vertex correction, like this, for example. So how am I going to compute it? What is the rule? I integrate overall momenta. None of these factors will matter, okay? I'm going to be very sloppy, just to give you a feel. So I need to know the form of the propagators of the Fermion propagator. Let's use the Fermion as a function of k is I. It's really irrelevant. K slash minus m. It's often written as k slash plus m. K squared minus m squared. We'll talk about it. Notice that there was always one and the same pole here, which is the propagator of the scalar field. Okay? And there is an interesting here. If you remember, this is the sum of the. This, if some of you remember, is u bar, the sum of the polarized states. A passing remark. Okay? I'll come back to it. So I'm interested in the high energy behavior. I want to know whether I can compute. I can compute if I don't get infinities. And typically the reason I may get infinities is that I am supposed to integrate according to this picture all the way to the infinite momenta. Now here's the catch. And there comes maybe the love of you for string theory, some of you. It's hard to believe. It will make no sense to assume that field theory will to infinite energies. Okay, that's asking too much. Even if you did believe, you see there is a scale at which gravity itself becomes strong. You're going to be learning about it. I come back to it when you know more and I can tell you more. At the moment, let me worry about this high energy without much ado. Then I don't really care on the low energy end. So you agree I can ignore the mass of the electron. It's very tiny compared to the integral I'm going to be studying. I'm going to be sort of integrating from 0 to some large number. So I could write 1 over k slash for the fermionic propagator. Let me ignore external momentum also. I just want to get a feel for what is happening in the loop. So I got two. And if I'm Feynman, remember, then out of the complicated photon propagator, I can just pick up the piece. We had minus I, and today we get a glimpse of y minus. And photon has no mass, so I don't have to worry here even. So what I'm going to get is 1 over k squared. We know that there are particular gauges, okay, we can call them Feynman gauge. This is the form of the propagator, okay. And here there is gamma mu in the interaction and gamma mu. This is just the Lorentz vertex. This is the integral I have to do with some gamma matrices in between. Is that clear? Okay, all I want to get a feel for the... so how I'm going to do it? Well, this is d3k. This is, sorry, this is k cubed dk, or k squared dk squared, 1/2, something like this. There is a phase factor, okay, proportion. Right. I don't care about factors of pi or anything. I want to emphasize the point here. Notice what I get. I get 1 over k to the, I will get k squared, dk squared, I'm sorry, proportional to, divided by k to the 4th. K slash square is k to the 4th. This is clear, right?
Yes. Yes.
This obviously diverges. But I'm going to integrate to some lambda. Remember, I shouldn't start from 0. I neglected the electron mass. There is, probably I should start from the electron mass. But I'm not worrying about the low energy end, okay? This is infrared structure. What I notice, that I get something that goes as logarithm of lambda square over me squared. I'll cut it off at me. I have to cut it off because I assume that the electron mass was 0. It diverges. This is the famous ultraviolet divergence of the of field theories. Okay, this drove people like this drove Dirac crazy. He couldn't live with that. What you do, what you will learn in the process of normalization, that you will even manage to get rid of these factors of lambda, okay, in a complicated manner. But I want to emphasize today that this is actually, this divergence is very small. Okay. It's a small infinity, if you wish. Okay, what do I mean by that? So how would my perturbation theory look like? I will have the original vertex was E, you agree? The charge is 1. So it would look like this, E, 1 plus, there'll be E squared, agreed? Well, I'm calling the electron, so let's call it psi, so that you see how confusing notation be that the electric charge will be confused with the name of the particle, which is the electron, okay? There are factors of pi coming from here, and you will get something like, typically people write 8 or 16. When the dust settles, it's not so important, it's a number, okay, and there'll be pi squared, and there'll be logarithm. So I put 8, because I'll take lambda over me. Please don't worry so much about this number here, okay, just I wrote it for fun. Okay, what is important, what I want to emphasize, that by any reasonable field for science, this is a small number. Why? Because logarithms are small. It would be crazy to think that physics that I know uses simple-minded QED is going to be valid to infinite energies. It won't be. Today, actually, we know when you hit the energies of 100 GeV, you have to include weak interactions. The thing gets more complicated. This is not the whole story. There'll be W in the loop and so on. And you and I, if we have any touch for physics, we believe that eventually, of course, the field theory will transform into something more profound. Okay. Just to give you a feel. In other words, I get a correction which is 1 plus alpha over 4 pi. These are famous factors that come out of perturbation theory. We are very lucky that what comes out is always alpha over pi, 2 pi, 4 pi, and this is a tiny number times the logarithm. Now remember what I said very briefly the other day. I will brief again because we'll come back to it when you finish the general relativity course. It's going to happen before I finish my course. How does the gravity looks like with these units that I have here? How does the gravity potential, let me write like that. We are used to talk about the gravity potential. Let me write here, V of R. Remind me, G Newton.
Over R.
1 over R. And here,
When
mass, m1 times m2. Actually, Einstein says that Newton is a little wrong. It's not just mass. Energy enters too. According to Einstein, and it seems that the guy was not completely stupid, okay? Gravity couples to energy. It makes light deflect in the sun, okay? It couples even the energy of the vacuum. You'll be hearing about that. Any energy in the world, okay? I don't care. Vacuum, which seems empty, could have some energy. Normally you don't care because I measure only the difference. Well, graviton does care. Gravity itself, it cares about everything, everything in the world. So I should really write E1, E2 here, roughly. That'd be correction to 1 over R and so on. What is G Newton in my units? It's simply 1 over m squared. Dimensionally, you can convince yourself. It's called m Planck. For example, this is gravitational. How would the electromagnetic, let me put this here. Let me use the blackboard. The original vertex will be corrected by alpha over 4 pi, logarithm lambda over me. How would the electromagnetic look like? It has 1 over R. Just like gravity, it's a long-range force, potentially, and it looks like E squared, 1 over R. There are no masses in question, just charges. Okay, I could write, just to be fair, between two charges, Q1 and Q2, it would have this form. So notice the relative strength. This is when I say that the gravity is very weak. What I mean that the gravity is very weak, it's equivalent to the statement that M Planck is, someone knew yesterday, about 10 to the 19 or 18 GeV. Depending how I define it, but if I don't put any factor scale, I'll get 10 to the 19. I like this more. It just emphasizes that the scale is large. Okay, I could put some factor here and then put it smaller. But anyway, just to tell you, okay, when I write it in this form, so at small energies, and look at what small energy is. A small energy of 10,000 GeV at LHC, the highest energy ever reached. Okay, you know what Large Hadron Collider LHC, Alexei must have talked about it.
Yes.
Related. The energy is
14.
it's the order of 10 TeV, which is 10,000 GeV. Sorry, 10 to the 4 GeV. That's a very small energy. Look how language changes. Compared to the 10 to the 19, that's 0. So even at LHC, people don't have to worry about gravity. Gravity is irrelevant. But you see, when the energy hits M Planck, one day, close when you come there, I won't be around. I'm afraid you won't be around either, okay, when that happens, okay, but as terrible as it sounds. But we'll have to worry about something we won't know how to deal with. We don't know how to deal with QCD at low energies. We simply have no way of making perturbative calculations. a reasonable cutoff of naive QED should be at least in Planck, if not before. I hope it's going to break earlier. I hope. Life is all about hope, and I hope you hope, so that the physics that you do will become relevant physics, and there will be some new exciting thing that you're learning now. I know that you will be learning the physics of the 50s of the last century, okay, or 60s, or 70s for that matter. Because basically nothing really happened afterwards in terms of the development of what we are probing today, sadly enough. So if I take the cutoff to be in Planck, which is to me extreme, there'll be new physics before. I'm dead sure. And mind you, when you talk of QET today, you cannot ignore interactions anymore. When you come to the energies of LHC, there are W's and Z floating around and crazy, and top quarks and whatnot. Okay. What would I get here? This will become 1. This is about 10 to the minus 3. And logarithm will give me logarithm of 10 is about 2.3 natural logarithm. Lambda over ME would be, this is 10 to the minus 3, this is 10 to the 22. Agreed? So I'll get 22 logarithm 10, which is about, I don't know, well, let's say about, I was Cavalier here, let me be Cavalier here, about 100. It's still a tiny number. This infinity is minuscule. And this is the crux of this, or the good theories that we call normalizable are all about. At worst, they get these logarithmic infinities, and we know how to deal with them. So, even if I didn't learn the tricks that you will call its renormalization of charge and so on, I would have to worry about tiny corrections under any reasonable assumption for what are my original quantities. I'm going to have to erase this, but you wrote it down. And of course it's in the notes, and every note, every book starts with this. So this interaction I can write is of the form. Remember I did yesterday, I said I can write this as 1 over m Fermi squared. And this will be psi bar psi squared, roughly. Okay? I want to emphasize the dependence on the fields. You agree? There are gamma matrices and whatnot. So how does it look like, this vertex? According to Feynman, it would look like this. For example, psi is entering, psi is going out. So I get psi bar squared. Suppose I want to do the same thing. You say, I'm getting ambitious. This is year 1957. If those guys manage to make such precise calculations, we ought to try to do it. This is how the loop would look like. I should close this loop, for example, here. And I have the analog of what I did here. There'll be a huge difference, though. Why? Notice immediately. There'll be d4k. Forget the factors of pi and whatnot. Because now, there you may have to worry just to estimate the number right. Look what we would get. There'll be just 2 fermionic propagators. And that goes as 1 over k squared. And this goes as k squared, dk squared. Typically what we do the Euclidean integration and so on. Okay, I don't want to go in the technical part. Okay, you're learning this with Sejanovic, right? You're learning how to do this integral. Okay, so what you do basically boils down to this, divided by k squared. What will I get now? I get lambda squared. I'm integrated all the way to lambda from whatever small number I'm taking. There'll be lambda squared minus something. Like if it was electron scale mass, it would be me squared. I don't write it because this is 0 compared to lambda. Lambda is at least above the scale of M Fermi, okay? And if you want to think today, lambda should be above the LHC energies. Well, let's go back to that era. In order to make sense, lambda must be much bigger than M Fermi if I want to do loops. Doing loops means that there is no new physics immediately there, because then you have to change your physics and start doing loops with that new physics, okay? So the cutoff here, I should have said immediately, must be much bigger than the electron mass, otherwise there is no sense of doing the loop. Okay? So look, the perturbation theory here would look like this. You would have the same interaction. The original term was G Fermi, 1 plus. There will be another G Fermi, right? There was G Fermi here, lambda squared. By very definition, this is much bigger than 1, by the fact that you are able to do the calculation. There is no perturbation theory you can do. It would break down immediately the scale of the Fermi scale. It would live very little. Okay. And why? Because you get a quadratic divergence. This is where we keep hearing we are scared of quadratic divergences, we hate them. And we like logarithmic divergences because logarithmic divergences are small. You understand what I mean by this? Small in the sense that I have a deep belief that there will be a cutoff in nature of naive theory I'm studying today. Otherwise, why the hell I'm doing physics if I believe this is the end of it, right? Why am I should be an engineer then, make more money, or an architect, or whatever. You and I want to make some discoveries, be part of that. We hope deeply that something will be revealed soon again. I was blessed. I studied PhD at the time when everything was blooming, okay? Blessing brings curses. I spent a lot of time in the desert of no physics. I'm a physicist. I need experimental results. I don't follow them deeply, but in order to do physics, we need to know what in the world is happening there, right? In nature. Anyway, so obviously, I'm forced to. It's not just the beauty of having a messenger. It's the practicability. It's the capacity to make computations. If I want to make computations to make more precise statements, I better imitate what these guys did. In other words, I say, by analogy with QED, that the weak-aligned Lagrangian, not effective, but fundamental, just like there, as the form J mu. I could have written this just to emphasize that. This is E J mu, electromagnetic A mu. Okay. By the way, please stop me, ask me questions, whatever. Make comments if you are getting lost or if you want to know more. So I would write J mu with a corresponding messenger. J mu, yes please?
It's about, I cannot define a potential analogous to electromagnetic, but for the weak force.
Yeah, sure, sure. It's one of the first pages of the notes. If you ever look at the notes that I sent you, actually derive the potential, the static potential for a massive messenger, okay? But let's guess it before doing the, it's not the moment, okay? This is a digression, I can come back to it so we can discuss it sometimes, okay? But let's, you and I try to guess it. What would you expect is the form for a massive particle? Why do I say that the force is short range? This is an excellent question. It's very important. It's exponential, actually. It turns out we should derive it, okay? Yeah. This happens, by the way, how do we arrive there? This is Fourier transforming 1 over Q squared. Remember, in the momentum space, the interaction goes as 1 over Q squared, so we have to do the Fourier transform in the momentum space to this space to get to 1 over R. Actually, it's easier to do the calculation by putting a small mass and take the limit m going to 0. It's in the notes, please. So it's the time to start looking at my notes. Okay. By the way, notes are just for your eyes, as I said. They're full of errors. I've never written a book that I was dreaming 20 years ago. I had even bigger notes on beyond the standard model, which I would love to teach here, not the standard model. I don't do standard model, obviously. I have there maybe even 200 pages. 20 years ago written. I never written a book. People have been after me, Cambridge Press, for years. But every time I start writing, then a new project comes, and I have this weakness. I get excited. And so the notes are not really clean. I'll be grateful when you find little errors, conceptual, some are typos, some are actually errors. You learn, you know, it's good to have errors. So, what turns out when you do the calculations, and I'll come back to it, you will get e to the minus mr, 1 over r. And they will be, but before I do that, let me answer it in a second, okay? J mu, which I raised, I'm sorry, he had charge -1. Can you check it? I'm pretty sure. There was neutrino, electron. Maybe I write it again, okay? J mu V is, there was a factor of 2. UL bar, gamma mu here, plus nu L bar, gamma mu here. So it has a charge -1, that means that the messenger carries charge +1. This is very different from the photon, okay? And this coupling constant, historically, it's called G over square root of 2. And often the people don't put the 2 in this factor, but put the 2 in the GF. Let's not worry about this factor so much. Depends how you normalize this thing. You can normalize it. Since this was the way I wrote it, let's say, at the moment, it's the form what is important here. We'll settle the factors soon.
One question.
Yes, please. First commission for you get.
I mean, like, just by commenting, because, like about the future, I mean, knowing...
I don't know what you mean. I'm sorry.
Yes.
You must tell me.
But I mean, pretending that we don't know, I mean, we know, I mean, we haven't seen yet in the class, but knowing that the Wing interaction is comes with like a gauge, non-abelian gauge symmetry.
Sure.
Local gauge symmetry.
Well, we don't really, we're just about testing that. Oh, be very careful. Non-abelian gauge symmetry requires testing the gauge structures. We are not there yet. This is just being done as you and I speak. There are strong indications that the standard model is based on a non-abelian gauge symmetry, but not proof yet.
But
we would bet, most of us, I will bet any money, but we don't know that yet. Okay, this is what you're going to learn here, to what degree we know that this is a gauge theory. Because gauge theory will bring some new, non-abelian gauge theory, what it really means. Okay, why do you think, so let me help you ask me a better question. Why do you think that this is non-abelian? Did you write down the non-abelian interactions? We say? So what's the main difference between abelian and non-abelian?
That they not commute.
What's the main difference physically? Don't give me mathematical explanation. You're a physicist. I need to get you to think physically, to answer physically. If there is a nice girl in the bar, you know, if there is a cashier there, she asks you, but what's the difference between the photon and these W's? Yes?
It's like the fields of the particles that intermediate these force.
Yes.
They
interact with themselves, just gravitons do.
Yeah.
You see what Einstein says, unlike Newton, that gravity interacts with gravity itself. It doesn't matter, even if there is anything that you put by hand, there is an interaction. You know, the theory is non-linear, sort of. So the main difference is that the gauge bosons interact with gauge bosons. That's just about being proven. This is a very delicate thing, and we are going to be discussing that. This is being studied at the LSE. So you and I don't know that yet.
Yes, we haven't studied that here, but my question
No,
is
not
that
here. You have never studied that.
Yeah, never.
This is being probed. No, I'm trying to tell you, this is being probed, and we have a strong prejudice that the standard model is the correct theory, but it's not. It's far from being proven yet. Actually, LHC cannot establish that the standard model is the correct theory. We will need to build a new collider. You must have heard of that. A good moment, since you asked me a question, to make a little digression. There are two types, maybe more, but two basically different types of colliders. Well, structurally you can make them linear and you can make them circular, but physically they are hadronic and they are leptonic. E plus, E minus, let's call them colliders. What's the main difference, you would say? Alexei probably talk about it. Which do you use to make discoveries and why? Which physically, which? What would you use, hadronic or leptonic, and why? Well, you can first say whatever you like. Hadronic. Do you know why?
Because they're made of stuff.
Right.
They're
You can accelerate, you can increase faster the energy of the but making a lot of turns you can get
But if it is circular, well, it goes like this. If it is circular, then it's better there is radiation is lost when you accelerate.
It has to be with
That's to me,
particles.
sure, that's secondary. There is one more, there is something more elementary I would like you to hear from you. You see, in a E plus E minus machine, or any machine, you fix the energy. So you have some energy of the machine, right? In A plus E minus, this is the energy that you are going to be probing. So if you build a machine that has 1 TeV energy, you will make discoveries at 1 TeV only at that energy. There is no way of varying the energy. Now, the beauty of the hadronic machine is that energy is not really very important. That's the maximum that you reach. The stuff inside doesn't carry that energy. It carries all the energies in the world. So the hadronic machines, which is type PP bar, or PP, and the reason is I can use PP because inside the proton, there are not only quarks. These are quantum mechanical states. They have, clouds of particles and antiparticles. So in all these machines, what I have is the quark QQ bar, and there is gluons and stuff. And they have all possible distributional energies. Therefore, I can make discoveries. Since I don't know with energy, things will take place. I prefer a hadronic machine. Once, however, I find something new, like the Higgs, I want to study the properties. The next step is immediate to build a... You start building, and this is being debated, okay, the W and Z bosons were discovered in a hadronic machine, a PP bar machine, SPS, in '83. And then, luckily enough, we got LEP, Large Electron-Positron Collider, which made all the high precision statements about the physics of WZ that you can look in particle data group, okay? And that will take to build a machine. So what I'm saying is I want to teach you the art of speculative conservatism, or conservative speculations, okay? That you don't take things for granted before they are checked, but you still make some attempts to make modifications, okay? So the reason I'm going through this history here to show you that at every step of its development, it is this physical reasoning that is very important that I will hope you will get at the end, that made progress continuously without any input from experiment. I want you to participate in the development, okay? I don't want you to do the way the books do, because then you get a feel. And sort of you get a feel of the clarity. And it helps you to read, when you read a book, to understand the material. It doesn't help you to understand how to think in the confusing stages when you are supposed to develop something new. And you end up very often with the thing that you read things which are clear, and then you jump and read to me things about strings which are so far, and you don't know how to deal with in between, okay? I want to sort of bridge this gap. This is the reason. So, without further apology, okay, I want to show you that I can mimic what Qe did is by having a messenger for the weak interaction. if it looks similar, not exactly the same, this square root of 2 is just historic, so I put it because it will emerge later in my units. And then, of course, instead of doing that, means that the interaction now is that there is a W boson, and then, for example, a down quark becomes an up quark, or vice versa, right? So what I have to do is a loop like this. Very similar to this thing. Before I do the loops, let's see how I would reproduce weak interactions. Well, it's very easy. Now there will not be just one point, right? There'll be where the interaction takes place, by whatever reason. There is an exchange of a W boson in a process in which, for example, a down quark comes, becomes an up quark. See, it's very different, however, from QED. I'm now changing one type of states to the other. It's not just scattering them off. So that means I am throwing the W minus here. This becomes an electron, and I draw neutrino entering. And you always remember that's equivalent to anti-neutrino coming out. Okay? And so the original words, how would the picture like? There would be UL, gamma mu dl. These are actually left-handed. I should remember that Marchak and Sudarshan experiments confirmed it, taught me that the theory is V minus A. They did it by analyzing the existing experiment. Discarded a few which to them looked wrong, and they were right. Hundreds of different experiments confirmed with great precision this picture. Then I get, what was the propagator? Do you remember? It was G mu nu minus Q mu, Q nu, or Q squared. No, I wrote it on purpose, okay. M squared, MW, let me write it. Usually the mass of the gauge bosons are written as capital, is Q squared minus MW squared. And here what I will get in order to complete, I need EL bar, gamma nu, nu L. Agree? I immediately reproduce the weak interaction because I'm at very low energies. What does it mean that I'm very low energies? That means that Q is much less than MW. Q is much less than MW. I get there will be G squared over 2. So let me write it just for the sake of completeness. There'll be G squared over 2. Remember that here there is a half hidden, so I will get 1 over 4 U bar gamma mu 1 plus gamma 5D E bar gamma mu 1 plus gamma 5 nu. Only G mu nu contributes, so I get this, and I get 1 over MW squared up to the sign of the amplitude, which I don't care about. I will calculate the cross section with the square. Not at the moment, we will worry about the signs, okay? There is 1 over 4 because the left has a half in the definition, okay? You follow me? Right, it's a little nicer, I'm sorry. This is G squared over 2 with my funny definition of G, 1 over 4, 1 over MW squared. And this thing is written as G Fermi over square root of 2. And it tells you this is not 24, so this is times 1 over 4.
And everything that we did in QED displayed here looks
like that. It looks like that.
For example, I can have loops inside.
You can have loops inside. So it seems. I'm going to come to loops, okay, in a moment, okay.
I can have even.
Yeah, you can draw anything. It's the same thing. Sure. You will draw anything that you draw before. You were drawing before, you will draw it now. There will be anything, and we'll discuss that. What I want to say is it's very easy to do this. I have to do here, I have to motivate you. I'm sorry, because you are saying, what's the big deal? I don't mind learning anyway, okay? I want you to try to get a feel or why it was good at that era to work on these things and risk your life, maybe years, career, sorry, not your life, years of your life, and that's somewhere. I want you to appreciate that the choice of what you're going to be working on ought to be thought through. Okay? Even if you don't do that, I will try to do that for you. I'm assuming that at least some of you are taking yourself seriously as physicists. You would like to be part of discoveries of nature. And that means the hardest thing is to try to guess which way to go. Once you know it, it's very easy. To a good degree. You learn the tricks how to compute and you go on. So it seems that I'm doing better than before. I'm now imitating QED. I immediately produce the result that Fermi wrote down, so I have no problem. I can ask you a question, how would I get the potential? Well, now it's not 1 over Q squared, it's 1 over Q squared minus M squared. So from here, when you do the potential, sorry, not from here, I already took U equal to 0. This will give me the potential, which I won't derive now, which is G squared over R e to the minus MWR. This form here changes the, and we have to be careful about the pole here and so on. We can do that. Have a look at my notes so that it's easier for you to follow. And this reproduces nicely QED in the limit M photon going to 0. There will be M photon here. By the way, this is how we put the limits on the photon mass. You look at the deviation from the 1 over R potential. This is typically the best way to go about it. There is not much improvement in the limits on photon mass. It's not being taken seriously. Everybody has a prejudice it's going to be 0. So, you know, experimentalists, unfortunately, live among men and they focus on things that look more hopeful. It would be good to keep probing that. It's very useful. As usually, the discoveries may come from you measuring better. And telling you, aha, here you go. Anyway, so let me pause here. Did I really do better than before? I have to do this loop now. If I had a up quark become down quark, then I can have correct it with another W. You ask me, can I draw it? Let me try. So this becomes down quark if this is a W, which then becomes an up quark, which I can do that. So what I have to compute, D4K, again just proportional to. I have two fermionic propagator, they are just K slash. Remember, I go to high energies. I'm checking the large momentum behavior of my loop. 1 over K slash, 1 over K slash. Now I have to write the propagator of this guy. Sorry. I forgot to send this one. Now the propagator is a little tricky. There is G mu nu here. Of course, there will be gamma matrices. I just want to see the form. Minus K mu over M squared. This is K squared dk squared divided by K squared. Notice there are two pieces. There are gamma matrices, so this is sort of 1. In the symmetric integration, there'll be 1 because there'll be gamma mu, 1. And then the other term plus something which is order of K squared over M squared. Agree? By the way, this is really in symmetric integration, this will become G mu, this is proportional to G mu nu K squared. Okay. So notice that the first piece, did I make some, No, there is 1 over k squared. Sorry. Times 1 over k squared minus m squared. I forgot the essential piece of the propagator. It always goes as 1 over k squared minus m squared. So notice that the first piece looks precisely like the photon. Because at very high energies, m is small. You know, when you and I already at LHC, W boson is almost massless. 10 to the 4 GeV has 100 GeV. Start to look more and more like the photon, okay, as we keep increasing the energy, okay. So the first piece, let me call this I, 1 and 2. So the first piece, 1 goes as logarithm lambda. I already checked that. K squared will give me logarithm lambda. Look at the piece number 2. This is k squared, dk squared over k squared. This piece goes as 1 over k squared.
Yes. K squared.
I put k squared minus m squared so that you see where it comes from. Then I have another piece coming from here, which is of the order of k squared over m squared. This power counting is very useful. This is giving you a feel. It's called power counting. You're just trying to, before doing the calculation, you're trying to see how it will look like. This is very useful before you start computing, okay? Whatever you do, try to see physically what you expect and so on, because often the mistakes will propagate in, and it's good to keep doing physical checks. So I want to see this will cancel, k squared. This I can take to be 0 for large cutoff. So notice that the k squared will cancel with a squared, and I'm going to get a number which is not logarithm, which is lambda squared over m squared. Okay, because this is dk squared is not being cancelled. So I'm back to square 1. I want you to appreciate there was a profound problem. This was realized. That this will really be a problem was realized to be not immediately, but it emerged. And so what you and I have to do, you and I, okay, this is now the standard model course, is besides the construction of the electroweak gauge theory, I have to learn. We have to do it together, how to cure this. After all, Jorge says, W exists, don't make such a big story out of that, it exists, let's just do it, okay? Nike commercial, just do it. Okay? I don't want to just do it, I want us to get there together. But I have to worry about that. I didn't improve the behavior of perturbation theory. I hoped I would. But this bloody mass of a gauge boson, it's not a trivial thing. It complicates life. So now, 1957, why in the world would you still pursue this? Now let me show you why. Why it's sometimes too good to do that. And then we'll just do it and learn the physics of massive gauge boson. You see, these things, if you didn't catch all the details, you would be coming back and back to us. But still, maybe you have a question before I summarize. What did I learn? I learned that I can imitate Fermi theory of weak interaction by the exchange of a W boson. But I'm so far from the mass of the W boson that looks like 100 GeV or so that you can say, why the hell are you talking about that? Okay, you're saying this to Schwinger. Actually, it's Schwinger. And the second thing, I cannot even do loops. Cannot do loops because they go as lambda squared. So in other words, remember about the perturbation theory. I will get corrections. In other words, I will get corrections lambda squared divided by nw squared. What I got to measure less numbers, okay? And this, by definition, will be numbers much bigger than 1. I cannot do perturbation theory. Okay, I really have to convince you that this is crazy, and yet it was good to pursue it, okay? It's crazy. It looks like a total failure. Now, and it's only a language. Because sometimes you get caught in the language. If you have a fancy language that cannot be tested and cannot lead to any new result, then you're using a lousy language. Please don't use Chinese if you can use English, because we all speak English, okay? Okay, that's the message that I have. And it looks that I'm using a wrong language. I'm not gaining anything. It seems that Fermi is doing better than me in 1957. He's using the language of what is going on, and he can make statements that are physically meaningful. Well, sometimes you decide to ignore the problem when you have a theory of what this, whatever new idea is. It's not enough to have a speculation. It's not enough to have a vision. It's not enough to have an idea. Unless you can follow it up with a well-defined, minimal, clear structure, the way Einstein did, the way Maxwell did, the way everybody did in the past, that made great progress, okay? It's just a language. So what changed things is that Schwinger's idea, he says, well, I'm still going to try to do it, but let me now focus what really made QED good, and that was the gauge principle. QED is good symmetry, we see, because of the gauge symmetry, because of that U1 symmetry. So why don't I try to imitate that? So U1 is equivalent to QED. What is the minimal symmetry I need to use for weak interactions? SU2. Why is it SU2? Why is not U1 times U1 or I don't know? How do I know it's SU2?
The number of generators?
The
number of generators in SU2 and the number of gauge bosons are the same.
Okay. But what's the difference between the number of generators? For example, in SU2 there are 3 generators. So you're saying, aha, I want to include a photon too. Okay, let's try to do that. Then I have 3 gauge bosons, 3 generators, W plus, W minus, and photon. Remember, there was no Z boson at the time. Okay. I'm going to show you how nicely it's going to work. Okay, but suppose I have a, for U1, gives me covariant derivative. Okay, call it E here. 1 gauge boson, 1 generator. You have 3, you said it has to be SU2, but for example, U1 cube also has 3 generators. And I don't have to learn the new structure of SU2. It's true that SU2 is nicer than U1 cube. How do I know it cannot be U1 cube?
Because of the charge.
Charge. The generator of U1 cannot have charge. The gauge boson does not know of charge. It couples to charge, but the guy itself is neutral. Okay. That requires a non-abelian structure. Okay. Here is, of course, and a few years before, Shaw and a student of Salam, who unfortunately disappeared for physics, and Salam did encourage him in Imperial College, and Young and Mills constructed what is called, what should be called Shaw-Young-Mills theory, but unfortunately it's called only Young-Mills. Okay, the history is never kind to people that sort of don't become heroes. Because, you know, learn some history, you will always see that there were other great contributors. So there is a non-abelian gauge symmetry. So why not use it? And it should be based by SU2 because W has a charge, and that will emerge from.
But
from
did we have any observations for this before? Then why would I want the?
Why would you want to do the gauge symmetry, right?
Why would I want the gauge bosons to be charged?
Yeah.
Oh, it has to be charged.
Why?
If it exists, it has to be charged because it's coupled to the charge currents. Remember, let's write again. Some funny coupling constant,
Yeah.
U bar, gamma mu, L, dl, and so on, coupled to W mu. Current carries charge, Lagrangian cannot carry charge. Charge is a good symmetry. That's one of the symmetries I'm not going to touch. By the way, it's good with extraordinary precision. And that maybe you should come and ask me one day, why do we talk about the precision of electromagnetic charge? I don't know if you ever ask yourself, everybody tells you charge is conserved. To what precision? Unless you back me with that, I won't make for the comments. It has to carry charge. Otherwise I'm breaking charge.
But they didn't have quarks at that time, right?
Okay. So what am I describing? Neutron.
Yeah.
So this current, they would have written as P bar, gamma mu,
Okay, yes.
and carry charge.
Yes.
No matter whether I use the weak current, by the way, is a violent. The weak current reflects that weak interactions are violent. They're crazy. They make you disappear. I mean, the weak interaction tells you that you and I should disappear. By the way, why don't we decay? It's one of the deep questions of nature. How come neutron decays a proton not? These are kind of questions that we can ask beyond the standard model, okay? Well, of course, you can also say the way you say to the child, shut up and eat your spinach, you say to, you know, when they ask you a hard question, and you were told, or whatever you were told, but the nice question that you can pose, why doesn't proton decay into positron? And I don't know, neutrino, or photon, or pion, whatever you name it. Okay? It's interesting.
You don't have a strong interaction with electrons.
I know, that's eating your own tail. I'm asking why is this not happening, you're telling me because it's not happening. If we observe this one day, we will learn that there is a new interaction that makes proton decay. By the way, everybody is looking for proton decay. For the last 30 years, the name of the game was looking for proton decay. Theoretical prejudice is actually that proton does decay. There is a theory behind that. It's called grand unification. It says proton must decay if you believe in grand unification, and that, of course, I will talk about when I come at the end of the course. I will, however, as I'm doing today, every now and then will be wetting your mouth to remind you that for every established statement there is a question we can open. And there are so many of them that what we have to learn the discipline to try to understand what we could focus on that could be meaningful. So not answering all of them, but anyway, at the moment we don't see that. What we see is this.
The pions. Maybe it would be
Yeah.
better to look at the pions.
Yeah, sure, pions could be there. SU2 means that the covariant derivative simply is d mu minus IG dA A mu A. This is what I mean by, I can put this index anywhere and put it down. It's irrelevant, okay? Because the Lorentz index is lower after are the same, okay? And what SU2 say that TA, TB. I have to do this, it's going to take us a few minutes. That means that the simplest, of course I have to define now, I define it by the structure covariant derivative, I have to tell you what it acts on. Okay, and what it acts on we call matter. Matter is, we know today, quarks and lepton, it was proton and neutron, as people are asking why. Proton, neutron, remember you will always get the same result, okay? It's just bookkeeping. At the moment, quarks are just bookkeeping for us. You and I don't see them. We call it matter for obvious reason, right? Quarks and leptons. But you can see, you're not being really systematic, you can tell me. You pretend that certain things we don't know, the other things we pretend we know, right? I pretend that there are, the quarks will be suggested in 1964, okay? I do this back and forth. Why? The things I pretend we don't know is the things that we have to learn how to develop the dynamics of. Saying that the proton is made of quarks is trivial. There's no dynamics there. It's just booking. You learn it in 2 minutes. But this is what is following. You're going to take weeks to learn. And the story is that the simplest representation, of course, that these are doublets in SU2. Yes. So we try that. That means that there is some up particle and some down particle. This may be up quark, down quark. Up here stands for up and down, which unfortunately also called up and down quark. It would be nicer to have other names, because I can be having a neutrino and electron, that's another doublet. Or if you don't like quarks, it will be proton and neutron and so on. So the interaction, obviously you will start with the Dirac Lagrangian and you make it covariant. It's all here. Right, the made covariant. Because I want to have a gauge. Just writing down what we did for U1. So this will give me I psi bar, well, when I write it, gamma mu d mu psi. And there is a minus I, so this will give me plus G psi bar gamma mu PA A mu A. This is the interaction of a Yang-Mills theory. Okay. This is the form. This is true. By the way, the only thing that changes here, if I go to some other group, epsilon becomes some number I call F. But everything else is the same. I'm going to develop, hopefully Saif will do that for me, but if it doesn't, I'm going to develop very carefully the Yang-Mills theory. We don't need it at the moment. All we need to understand what's going to happen now in the SU2. So what do I get? What is TA? When I say that they are spinors, they are Pauli members. So this becomes G, U bar, D bar, and then I'll have sigma 3, so that's A mu 3, there'll be G over 2 outside, minus A mu 3, you agree? Sigma 3 is diagonal. The usual convention I make as everybody else, as Pauli did. And what will I get here? A mu 1 for sigma 1, and A mu 2 for So what am I going to do? What I get is G over 2, U bar gamma mu. So I pick up this. Let's see if you agree with me. A mu 1 minus I, A mu 2, D. I'm picking up the off-diagonal piece here. Plus, there is an opposite piece when I go from here. I'm separating the diagonal and off-diagonal pieces, so I can write here U bar gamma mu U minus D bar gamma mu D times A mu 3. I've decided to ignore the fundamental problem of me doing calculations with a spin 1 particle because of the beauty of what the gauge theory does. It immediately brings in the interactions. Okay, if there is some SU2 gauge theory, so if you like gauge principle, you get a profound outcome automatically. This exactly G over square root of 2 U bar L. Well, I didn't write L, I'm sorry, we wanted them to be left-handed. Well, let's not do that yet. U bar gamma mu, D, W mu plus, where W mu plus is A1 minus I A2 over square root of root. Why do I put a square root of 2 here? To keep the normalization. Okay. And this is why G over square root of emerged. Okay. This in SU2, it's an automatic thing because I call this G. If I call this 2G, then, or square root of 2 times G wouldn't emerge. But it's natural to call the coupling G the way we call the integral 1. So I get immediately the form of the W boson if I, of course, assume that the doublets are left-handed. Now, what Schwinger was hoping, he's forgotten in the history, that maybe he could unify weak and electromagnetic. 3 gauge bosons. If he wants to do that, then this would have to be the The photon.
Photon. Yeah.
Let me write this in a more elegant way. I can write this as G psi bar gamma mu T3 psi A mu 3. Because T3 is sigma 3 over 2, which is plus or minus a half. You agree? It's just a more elegant way of writing the same thing. And we know immediately he failed. He had to fail. These are not the charges of... Because everybody in the doublet will have the same charge, which is either half or minus half. This is the beauty of SU2, by the way. And one feels, when I first saw this, I saw it later, I felt that it's one of those things that, I don't know who said it, I think it was Berlioz. But the great tragedy of science are the beautiful theories killed by ugly facts of nature. This looks like that example. This is a beautiful theory because it predicts all the charges. For example, quantization of charge is automatic. The miracle of quantization would work immediately because then bigger representation will have 1, 3/2, and so on, and you quantize them. It's just you quantize them wrong. It sort of makes you be angry at nature. You know, why didn't nature profit from this beautiful thing? There may be an answer to that. As beautiful as the idea itself, which is called grand unification. You will hear it in the last lecture of the course. But at the moment, it's kind of sad, and the Schwinger stops here and cries. I don't know what he did. Schwinger had a good student who was not completely stupid, by the name of Glashow, who actually did a PhD, then went on to be at Harvard with Schwinger, and then went on to be a postdoc at Copenhagen. And there, in 1961, he decided to take this seriously and cure it. Okay? And the rest is history, as we know. So, as I'm about to finish, let's summarize. And let's open the door for the new developments. If I want to have physics of electroweak interactions, this cannot be a photon. So maybe you could say, why are you not courageous and say that this is a new gauge boson? So maybe SU2 actually is a gauge serial weak interaction, and A3 is some new gauge boson called Z. This would be very good because you see you would cure immediately another problem. If these are weak interactions, this has to be left-handed. Everything had to be left-handed. In other words, my original multiplets would have to be left-handed. I can do that, but I cannot. I have to choose. Are they left-handed or they are both left and right? Okay. I have to choose it to be left-handed because I want to reproduce the weak interaction. That was my motivation. So this cannot be photon for another reason. Not only the charge is bad. Photon doesn't couple like this. Okay, so I say, well, that's good, because this is Z boson, and the theory of the world is SU2 weak times U1 electromagnetic. And let me pause here. Is this possible? I'll help you. What does it mean when I write SU2 cross U1? That means that there are some generators TA here, 3 of them. Some generator here that you and I will call Q, electromagnetic. But what does it mean that it's a direct product in group theory? That means the TA commutes with Q electromagnetic.
Yeah.
Otherwise you can't write it as a direct product. The direct product of any two groups means the generator of these two groups commute. Okay, that's very important. I don't want to work with anything. You see, the symmetry of the world is obviously, and I'm assuming that without telling you, that the symmetry of the world is some internal symmetry times Lorentz symmetry. Times they commute. So I even don't worry about Lorentz generators when I talk of SU2. Why? Because it's outside.
Yes.
Like SU3 color. This is the reason why I don't talk about SU3 color. It commutes with this. I can forget about it when I'm talking about weak. If they don't commute, if Lorentz is this side, all hair breaks loose, right? I don't want to touch that. But Paul, is this possible? help you? It's not possible. Why? Because what does it mean that they commute? That means that the particles in the representation will have the same charge.
Yes.
Otherwise, they wouldn't commute. They don't have the same charge.
Can you repeat that, please? Can you repeat that, please?
Sorry?
Can you repeat that, please?
I'm saying that this statement, equals 0. This is equivalent. What do I? They direct product means that they commute. This is equivalent to Q up equal Q down. That's what it means that it commutes. You cannot distinguish them, otherwise it wouldn't commute.
Yeah.
Otherwise, it would take you from one charge to another. But it commutes, so the charge must be the same. That's not true.
The weak charge.
No, the electromagnetic charge would have to be the same.
Yeah.
No, because I'm saying that this commutes with this. It's outside.
Yes.
You see, when I tell you that spinners, this commutes with Lorentz group, that means that when I do the SU2 transformation, spinner stays spinner. That's whatever you've done up to now. That you may have not thought about that. This is built in the very crux of the theories we are studying. Okay. That means, for example, the W. What does it mean? It commutes with strong interactions, the weak interaction. The W can take a quark into a quark, but not into something else. And that's why I can forget about what strong are doing, or what Lorentz is doing. The same thing. Spinner must remain spinner. In other words, photon cannot take an electron into a W, even if they have the same charges. Well, a photon is so delicate, he cannot even, or she, take an electron into a muon, which is almost the same. No, this guy is really conservative, okay. He just takes an electron, he keeps it an electron, okay. W is violent, W takes up to down.
Yes.
But W here would be outside the U1. The groups would commute these generators, okay. So I want these charges to be the same in this picture, but it cannot be. So this is what is the great thing. Why it was great that Gleshow pursued that in 1961 comes Gleshow. Because now you learn, and the theory must be SU2 cross U1. SU2 didn't work. The minimal group, I want to realize my idea of whatever idea it was, and it was a gauge principle. The realization must be minimal. Otherwise, why talk? If Einstein didn't write the minimal theory, there would be no prediction whatsoever, okay? So when we say that the symmetry of the world is SU2 cross U1, that means that this is not a photon, this is not electromagnetic. This is often called hypercharge. Here one puts L to emphasize that the weak interactions are left-handed, but it tells you that the charge must live here and here. We kind of unify, we put them together. And this is interesting to pursue. Now I have a deeper theory. It's not just weak interaction on one part and electromagnetic. This is the first attempt towards unification. We are now going towards Einstein's dream. Then maybe I can have one. It's always good in physics when I have one description of apparently completely different phenomena. That's what physics is about. And that's what I want to focus on in the standard model course. And not why numbers are what they are. That eventually you will ask me, and everybody talks about why the charge is what it is, whatever. No, I'd like to unify dynamics. Well, this is not done by me, so it's easy to talk like that. That must be some linear combination of the Neutron generator of SU2, which is T3, plus some linear combination of this hypercharge. Good time to stop. And to give you now a feel, I will be developing the structure of the standard model in weeks to come and the theory of the gauge bosons. You know how to live with spinners. You know their propagators, you know how to compute with them, you did QED or you're doing it now. Even scalars you know how to do. What you and I don't know is the physics of gauge bosons. We have to understand that in a deeper manner. At the same time, we are going to pursue this picture and construct the standard model. so that I keep the physics alive. But next 3 or 4 weeks will be mostly techniques. Physics will be a bit in the background, I'll bring it in, and then it will come back. Well,
But I have a question.
please.
Why did you change the U1, not the SU2 itself? I mean, we could have kept U1 to be the electromagnetic and SU2 to some other SU2.
It's a good thing. I've tried SU2. Didn't work. So there are 2 routes. One is add U1. The other is go to the bigger. So what would that be? Help me. When you ask me why you didn't, let's be more constructive. Well, take a bigger symmetry without U1. Actually, it's a very good question. That I don't know if you know how good the question is. Maybe you know, maybe you don't. It doesn't matter. It's a very good question what Asif is asking, because there is a beauty in not having U1. Then there are commutation relations that give quantizations. Or if you wish, maybe to give some deeper meaning. When you say that you have some SUN symmetry, that's saying that something, some wave function, some fundamental representation, which we often call spinors, generalization of SU2, transforms as U psi. So that U dagger U is 1, U dagger. Now I'm reminding you SU2. And that what? The determinant of U is 1. This is SU2. It's SUN. This means that I can write U as e to the I h, where h is Hermitian. A telegraphic review of group theory. This is almost all you need. This here implies what? Determinant of U. You will see immediately trace of H is 0.
Yes, trace of H.
So this is what the SUN symmetries are all about. That means that I can write H as a sum of some basis, dA, and some associated, what we call Euler angles parameters, right? In SU2 there are 3. SU2 is like SO3, there are 3 parameters, we call them Euler angles. But anyway, and this can go to as large numbers as you like. By the way, how many generate this SUN? Do you remember?
N squared minus 1.
N squared minus 1.
There are n squared minus 1, so I goes to 1 to n squared. So that TA dagger is TA, and trace TA is 0. This is the basis of Hermitian traceless generators. Okay. They're always traceless. See, this tracelessness gives you this quantization. It cannot be arbitrary, the normalization of charge, the relation of charge, the properties of charge. They must be summing to 0. This is responsible, of course, in the commutation relations. And in general, what you have, TA, TB, then is some commutation relation. And obviously, by having commutation relations here means that FABC is antisymmetric. But this is fundamental, the tracelessness. So this is why it would be better not to have U1, I agree with you. Because with U1, I will never understand why charge is quantized. This is why the death of SU2 was said. Because that would immediately tell me that charge is quantized. This extraordinary record. And I, for one, would have been happier. So then you could go on, and then you would have to go to something like SU3. That's the minimal extension of SU2. There is no group in between. Now, what is more minimal? It's an interesting... do you count just the numbers, or you look at the structures? This apparently is more minimal because I have only 4 generators if I take SU2 cross U, and this gets 8. On the other hand, SU3, you could argue, well, don't just count the generators, there are structures also. It's a question of taste here. What you would learn, why it didn't happen, when you try to construct SU3, Weinberg later on would actually try to construct a modification of the standard model. He doesn't talk about it because at some point people had doubts that the standard model didn't like to work. In 1977, he had problems with experiments. Then people that tried to modify, especially the fathers, didn't like to remember that because Nobel Committee may not like that. It turned out that if you want to do SU3, you still have to add U1. It didn't work, SU3. Otherwise, I would agree with you. It would have been an interesting an approach, okay? And if you keep having that question, you and I may try that when we learn enough group theory to see why SU3 doesn't work, okay? This is an art of model building. In many ways, this is the ugliest possible extension. Just stick U1. Then it's kind of trivial almost, right? There will be no commutation relation. Any questions?
I wanted to learn more about group theory. I wanted to understand more group theory.
So maybe I didn't understand about the hypercharge. So weak interaction doesn't modify the hypercharge.
Yeah, weak interaction doesn't know about hypercharge. Weak interaction is completely, for example, the first statements I will then make that the hypercharge of these two guys must be the same.
Yes.
It's completely orthogonal. It's like...
Okay. And that's because of commutation of the generators.
This is because this actually is not true. So this cannot be true because they do not commute.
Yes.
Okay, electromagnetic charges. They surely do not commute. You will.
With hypercharge. Sorry.
With the hypercharge is true. What I mean that. So I had to abandon that, and what it works. You see, I mean, I don't know if that was so much clear to you that TA must be 0. But you've been using it all the time. For example, when we talk about SU2 and I say that this is up and down, why the hell do they have to be both spinners? Because Lorentz must be commute. You're assuming that always. You're saying, aha, Lorentz commute with this, so if this is a spinner, this must be a spinner. Commuting means it's completely outside. It cannot change one particle into another. Okay? It lives in its own space. And that's why when I talk about SU2, I don't worry about Lorentz inlet. You and I would go crazy. I suppress Lorentz inlet. I suppress color. For example, that means that photon must be colorblind. If there is a red quark, photon only can keep it red. It's not going to change red to yellow. Otherwise, what the hell I'm doing here? I'm wrong. I can't work. So this is inbuilt always in you. Please think about that. This is completely equivalent to SU2 of weak, which I call left, is a direct product with U1 aperture, which immediately implies this.
Yes.
Remember, this is diagonal.
Yes.
Just collection of charges. So it must be only. It can only be the sum of the. Okay. That's it. I can go wash my hands. Those of you who have more questions.